Thank you very much. So yes, greenhouse gases are back on stage. I'd like to thank my partners for this new page of the greenhouse gas chapter, TNO in Amsterdam University in the Netherlands, and NILU in Norway. So yesterday, if we use the vocabulary of space agencies, we were dealing with level 2 data, starting from the spectrum measured from space, inferring the concentrations of greenhouse gases. And here, we are dealing with level 4 data, starting from the concentrations, inferring the surface fluxes that generated them. There are lots of processes that emit or absorb these molecules, carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O, at the surface of the Earth. They are schematized here in these cartoons prepared by ECNWF. Given the type of observations that we use, atmospheric concentrations, and the information content of these observations, we are not able to distinguish between all of them, except for methane, where we are able to distinguish between wetland emissions, right field emissions, biomass burning emissions, and other sources, so basically the rest. We have products that we update annually, up to 3 to 4 months every year, depending on observation availability. And of course, it's easier when it comes from space. We have products that, of course, are available on the atmospheric data store. There are many users of these products, but over the years we have worked a lot with the Global Carbon Project and the various initiatives that it has triggered. Most prominently, the regular global synthesis. For CO2, it's every year, so that influences a lot our delivery schedule to be ready to feed this global synthesis on time. We have one update of the methane synthesis from the Global Carbon Project every 2 to 3 years, and so far only one has been done for N2O. But we are always there to provide data and to partially lead all these initiatives, or actually fully lead them for some of them. There has been the RECAP and RECAP 2 regional synthesis, so it's basically one every decade, so not too hard, but important customers. And through the Global Carbon Project, we were able to feed data to the assessment reports of the IPCC. What has changed in our landscape is the rise, or the tentative rise of the UNFCCC through the global stocktake of the Paris Agreement. So I don't mean that UNFCCC is asking for our data desperately, but at least we are trying to tailor our data so that they can be used by the UNFCCC processes. In particular, through the global stocktake, which is a big political event prepared by a very ambitious data collection phase. And we want to have a prominent role in this data collection. We have been participating to 3 initiatives. There is the COCO2 initiative, which is ongoing, the RECAP2 initiative, which is dedicated to the global stocktake, and we have led this one, and the CEOS initiative led by NASA, which is being finalized. This implication towards the global stocktake means that we have more data to assimilate, because the global stocktake has motivated space agencies a lot, but also for us it means a new emphasis towards country scale. And this is important because we are dealing with wind patterns that are usually decorrelated from administrative boundaries, but we try to have product at this scale, even though it's not, I would say, natural compared to the product that we have. And also, since countries go down to the scale of, say, Vatican City, we want to have an emphasis towards higher resolution, even though we process the whole globe. Mentioning VIP users, of course the list is not closed, and if there are more to come, we will be very happy to adjust our delivery schedule and also our products to the needs of these users. In the rest of the talk, I will update you on the various products that we have, going through the species one by one, CH4, N2O, and ending with CO2. Starting with CH4, the new thing here currently happening is the release of version 20. Version 20 means that it will end in 2020, so it's being released right now. The competitions have finished, the documentation is being made. We have, as usual, two data streams, one with just the surface observations. It allows us to start in 1990, where the surface measurement network is enough to provide some resolution at the on the horizontal scale, and ending in 2020. The other data stream that we have combines the surface measurements and the satellite data from GOSAT. It starts in 2009. The major change compared to the previous releases of this methane product prepared by TNO and Amsterdam University is the change of the prior emissions from EDGAR version 4 dot something to version 6. Version 6 has different features. One of them is for methane. One of them is that it's higher by 30 teragram per year on an average compared to the previous inventory. So that shifts basically our prior emissions, so before the inversion, by nearly 10%. So there are other things that change, so it's not just 10% everywhere, including in the posterior. There are compensating factors. In terms of the posterior emissions that you can see here, in red it's the surface stream, and in green is surface plus satellite. You have something which is consistent between the two data streams and also consistent with the black line, which is the prior emissions. One exception is the last year of the time series, 2020. We infer much larger emissions than in the prior inventories, combining EDGAR but also model data for wetlands. It's not unexpected, but we also acknowledge the fact that our chemical sink for 2020 does not contain the lockdown signal. So maybe this increase that you infer for the methane emissions in 2020 is too high because we had too much of a sink in the atmosphere. So that's something that will be investigated. Another difference between EDGAR 6 and the previous version is that we have much more information on the seasonality of the emissions. And also, compared to what we have, the seasonality is also more in phase with what we have in the previous inversion. So not in the prior, but after the inversion, we had a seasonal cycle that was quite different from EDGAR. And now the prior in EDGAR is quite similar. As a result, we do not change the seasonality of the emissions anymore, or hardly any change anymore, which I think is a good thing. Another change that was added in this inversion data streams, the new release, is the change in the chemical sink. So I said that we still have an issue for 2020, but that's very recent as data, and it's very difficult to keep up to date with the evolution of OH. But a lot of work has been done by TNO and Amsterdam University to have a homogeneous time series with the best information about OH that they could get from the CAMS groups, and in particular correct these low OH concentrations that we had in the previous release. So now we think that we have something which is much more realistic in the tropics in particular, and of course it has an influence on the outcome on the inferred emissions. There is more in the pipeline for the next release, or not the one being delivered now, but the one that will be delivered by the end of this year. And quite a lot of changes. There is the possibility now to optimize both the emissions and the atmospheric sink of methane, so the OS concentrations as a global average. So that could make quite a difference, and in particular solve or partially solve the problem that we possibly have in 2020. We have been working a lot with GOSAT, but now we think that we are ready to assimilate YASI and Chopomi, and that will be done in separate data streams. Current results comparing or looking at the anomaly between 2020 and 2019 show similar patterns, whether you assimilate Chopomi from SRON, YASI from RAL, or even the surface data, even though with the surface data we don't have many stations and the signals are less pronounced. But overall, a good consistency, and all these products will be delivered next time. We have a challenge that was posed to us by ECA and WF in our contract. We have the target to move to a much higher horizontal resolution. Currently for methane it's 3 times 2 square degree. And ECNWF asks us to move to 1 square degree by the end of the contract, 2023. And we are working hard in this direction. One important step was the implementation of what we call the physical parallelization that was already operational for CO2, but it's really new for methane. It allows to add another layer of parallelization on top of MPI and OpenMP. We have a way to simplify slightly the transport of a long-lived gas like methane so that we can use parallel chunks for the transport computations. But more is needed, and in particular, some work has been done to analyze the runtime efficiency of the simulations at this new high resolution. And in blue, you see the share of the input-output data. It's not a surprise. We have offline models like TM5, and they use a lot of input-output. We really need to bring this blue box down. I mean, this is as a function of the number of CPU used in the simulations. We need to bring it down. In particular, we are testing, or TNO is currently testing XIOS, a software of asynchronous input-output that has been developed at LSC. Moving to N2O, that will be quite fast because we are slightly too early in the process to have the new N2O inversion. So this is the one of last year, and I presented these results last year already. The only thing that I wanted to emphasize here, so we are here at version 19, ending in 2019, and current computations are extending it to year 2020. The only thing that I want to emphasize is really the fact that we are penalized for N2O by the lack of observations. We have tried, I explained that last year, to use YASI observations for N2O, but we had great expectations. We have been quite disappointed so far, so we have to rely on surface measurements. And as you see from the uncertainty reduction, surface measurements, they provide us with information mostly in Northern America, Europe, and East Asia. For the rest of the globe, it's really, really limited. Still, we are able to infer time series in large regions, and they seem to be consistent with the uses of nitrogen in agriculture, but I said that already last year. The key thing for the current computations, extending the data set to 2020, is the explanation of the enormous increase, or the exceptional increase of N2O in 2020. It's the highest on record. This is a plot by NOAA. And looking at the Hofmöller variations over the years as a function of latitude, this anomaly, this exceptional anomaly, seems to originate from the high to mid latitudes of the north. So current computations are running. This is just a preliminary result, some iterations through the minimization of the cost function. It seems to indicate that the anomaly comes from the high latitudes, and this is consistent with what we understand from the physics of N2O, and we think that it could be reasonably linked to the strong positive anomaly over Siberia in 2020. But this is work in progress, and you will, if you stay tuned on the ADS, you will be able to look by yourself in a few weeks. Ending with CO2, I mean, this is the key figure that we've been highlighting over the last few months, and the previous version I showed last year. This is the comparison between the inversions. The long one, driven by surface measurements, is the blue curve starting in 79. And in orange, the OCO2-driven inversion, so that's the NASA satellite, OCO2-driven inversion in orange. There we have 1 sigma error bars, and the differences that we see between the orange and the blue are well explained by the 1 sigma error bars, which seems to highlight the robustness of the products that we provide. The results here are per large country or groups of countries. We have the EU and the UK. For the rest is Brazil, Canada, etc. Down the USA, here by alphabetical order. So that's an illustration of our new emphasis towards country scale. We also have in green, if you can see it, the numbers reported by UNFCCC, by the countries themselves to UNFCCC. We think that we understand why we have differences. between the green and the rest, and R curves, and we think that R curves are more realistic than the curves from the countries for various reasons. In the pipeline, we have an update of this figure, of course, in particular with satellite data. The results are still being computed, and I'm showing here an update with 20 iterations on a total of 40. So we are halfway through, and you see a major change in the product because we are now able to extend the satellite time series down to 2010, because in our tests we see that the GOSAT data as processed by NASA, that's the ECOS product, has reached sufficient maturity. That's excellent news for us to reach the elite and be used as really a reliable product for the inversion. So we will cover more than a decade now with the satellite data stream. And in this preliminary plot, preliminary result, you see that we again have a nice consistency between the blue and the satellite data stream. Look at Kazakhstan, for instance. I think it's really, really nice and really encouraging. We also have a high-resolution challenge posed to us by ECNWF. I prefer for CO2 to express it in kilometers, so instead of 1 square degree, I'm mentioning here 100 kilometers over the whole globe. It makes sense because of UNFCCC, but also it makes sense because we know that we have from the satellite data much higher resolution patterns that are realistic, like for here this plume originating from the ancient city in China, compared to the very coarse resolution of our global model. So we think, well, of course, we will not capture this with a 100-kilometer model, but this is just an illustration of what we are aiming at. And ultimately, yes, we want to have, maybe in 5 years or 10 years from now, we want to have a model, global model, that is able to capture that. To achieve this 100-kilometer resolution, we have a clear roadmap. We want to speed up the current offline model. We want to move to a hexagonal grid instead of a Cartesian grid with rectangles, so that we save 25% of the grid points. That's as much computations less. We want to use the asynchronous I/O server, XIOS, that I mentioned before, and we also have technical developments for tangent linear and the joint of the hexagonal advection, plus various piping work. So a very busy schedule ahead of us, but we are on good track. This is the forward model, nudge to ERA 5. So it's the full model, the online one, from which we take air mass fluxes to run the offline model. And this is run here with the Cartesian grid and at the same resolution, or roughly, run on the hexagonal grid that we have. Look at what we have, for instance, over Central America. We are now able to provide these computations on this new grid. So in good shape. Comparing to surface measurements, comparing the two grids, it looks really similar. I mean, this is Cold Bay in Alaska. We have something which is very similar, as could be guessed from the overall similar shape of the two maps. We seem to have something very in good agreement, but look at the minimum. It's shallower with the new advection scheme on the hexagonal grid, and we are currently tracking the differences to understand the impact of this new grid and on the new advection scheme. So, yes. It's my last slide, I think. Transport model, it's twice as fast now. Hexagonal grid is done for the dynamics. Asynchronous, hexagonal grid done. Tangent linear and a joint, it's ongoing. And I'm done.
It's a very interesting talk. Okay. I suggest, in the interest of time, we move on to the next agenda item, which is a report from the discussion on the emissions, I believe. So, Hugo,